Okay, geometry students, I appreciate you finding time to get your notes taken care of tonight. We are switching our discussion a little bit away from congruence and starting to look at similarity. So let's get started. Our objective for tomorrow's class will be the student will learn the definition for similar polygons and discover the properties that accompany that definition. These are the notes for Tuesday, November the 12th. Copy down your objective and your date. Press pause anytime you need more time, and then hit play when you're ready to move forward. Now, you probably have spent some time talking about similar polygons back in junior high, but like some of the other things that we did in junior high, you probably have an incomplete definition, and now we're going to fill in the blanks a little bit. So let's get to it. Okay, we've learned from previous classes that the term similar polygons means shapes with the same shape but with different sizes. Okay, now that's probably what you learned back in junior high. Okay, but again, everything that we're doing in geometry, everything that happens for a particular reason. So there's got to be something mathematical that causes two shapes to have the same shape but have different sizes. And just like with congruent polygons, there's actually two things that cause this. Okay. The first thing that causes it deals with the corresponding angles. Okay. And just like with the congruent polygons, we're going to want our corresponding angles to be congruent. Okay. Now, we talked about the corresponding angles being congruent when we did the congruent polygons, and we said this is actually what causes two shapes to have the same shape. If you start allowing corresponding angles to change measurements, that is going to change from rectangles to parallelograms, squares to rhombuses, stuff like that. So our corresponding angles are still going to have to be congruent, but the difference is going to be with the corresponding sides. Okay. With the congruent polygons, we were interested in the corresponding sides being congruent. With similarity, we are only concerned that the corresponding sides be proportional. Okay? Having them be proportional is what is going to allow a figure to change size as it moves from one figure to the next. Okay? Now we're going to have a little bit of a quick review. You probably don't need to copy down this next slide, but definitely follow along. Okay, from our discussions of congruent polygons, things correspond from one figure to the next, not because they sit in the same place, but because the locations share the same characteristics. Okay, and we examined a couple of triangles that were in the first example where they were sitting exactly in the same positioning, where we could say something like the top corresponds to the top and the bottom left corresponds to the bottom left and stuff like that. But keep in mind, corresponding, when we're talking about polygons, does not mean top to top and bottom to bottom and stuff like that. Things correspond because they have characteristics in common from one figure to the next figure. So it really doesn't have anything at all to do with how the polygons are sitting. Okay. Now on back to the definition, we talked about the corresponding sides are supposed to be proportional. Now, I hope you have a good idea of what a proportion is, because we're going to need to know that in order to do the math involved with proving similarity. Okay. Now, definition, if you do not have a definition, is proportion is two ratios that have been set equal to each other. Okay, two ratios that have been set equal to each other. And if you are not familiar with what a ratio is, well, a ratio is just a fancy word for a fraction. It is two numbers that are typically being compared in fractional form. There's actually other ways to write down ratios, but we're going to be worried about the fractional form here in geometry. Okay, so the basic format for a proportion, which is probably the one that you have seen over and over again and we will work almost exclusively with, is this guy here on the left side. We have two fractions that are equal to each other. Okay. Now the way that you read this is, and it's written over there on the right side of the screen, A is to B as C is to D. So a fraction bar is actually read is to, and then an equal sign is read as. Okay. A is to B as C is to D. Okay. Now, another way that you may see proportions, and it's not the typical way, but I want to make sure that you're exposed to it just in case a problem gets creative and decides to come at you this way. Okay, this is called colon notation rather than fractional notation. Okay, and it is still read identically to the fractional notation. A is to B as C is to D. The difference is the fraction bar is replaced with a colon, and the numerator is on the left, so you get numerator colon denominator equals numerator colon denominator. Now, hopefully you have worked with the math of proportions, so this next part won't be anything new to you either. Okay, working with proportions is easy enough. Now, guys, this is the only case where you ever get to cross multiply two fractions. And I'm not sure what happens at the junior high levels, but it seems like there's whatever they're teaching or however they're teaching, boy, it just gets y'all gung-ho on cross multiplying fractions. Y'all want to cross multiply fractions every time you see them. The difference is this is the only time that you're ever supposed to cross multiply two fractions is when they are separated by an equal sign. And that's what we have right here. So we have a proportion, okay, and we're going to evaluate whether or not this proportion is true. And the way that you work proportion or evaluate a proportion is we cross multiply. Okay, so we cross multiply over the equal sign, meaning the numerator from the left is going to multiply times the denominator on the right, and vice versa. The numerator on the right multiplies by the denominator on the left. So we have a little bit of math and a question. 3 times 19, is that equal to 8 times 7? If it is, then our proportion is good. If it is not, then our proportion is bad. Well, 3 times 19 is 57, and 8 times 7 is 56. So right now we have a statement that says 57 equals 56. Obviously, that is not true. So what does this mean? It means the proportion is not set up correctly. Okay. Now, one of the things that we're primarily going to be doing with our proportions is we will be cross-multiplying to check to see if the proportions are true or not, but we will also be using proportions to solve for an unknown piece of information inside of the proportion. So that's what we have here. 4 is to x as 5 is to 11. Okay, so if we wanted to solve it, okay, well, we need to cross multiply so we can get x going and solve for x. So once again, we'll cross multiply. So 4 times 11, and that will equal 5 times x. Well, obviously 4 times 11 is 44, and 5 times x is 5x's. Okay. Well, we do not want 5x's, we only want 1, so clearly the next step would be to divide both sides by 5. And 5 goes into 44 8.8 times. And absolutely, it is possible for variables to equal decimal points and fractions and things like that. So do not think that just because you didn't end up with a whole number that you did not get the correct answer. But just like any other problem in algebra, we have the ability to check this value. We think x is 8.8. So if we plug it back into the original proportion, this ought to tell us if it is true or not. Cross multiply again. 4 times 11, 44. 5 times 8.8, also 44. Does 44 equal 44? Well, of course it does. That means we have arrived at the correct value. X equals 8.8. Okay, well, enough of that. proportions have to be set up a certain way. And as long as the proportions are set up for us, as they have been on the last couple of slides, this is very, very easy to work with. The problem is, most of the time, the proportions are not set up for us, and we are going to have to set them up ourselves. Okay, so it's going to be up to us to install the information into the proportions correctly. Otherwise, we will get the wrong answer, and unfortunately, we will have no way of knowing that we are wrong. Okay, so I'm going to start with an example here, and we're going to look at this example in great depth. Okay, so copy it down if you need to. We're going to be talking about it a good bit. Not if you need to, do copy this down. Okay, if we are interested in trying to prove whether these triangles are similar or not, it's going to be necessary to prove that their side lengths are proportional. Okay, and the basic rule for similar polygons is this: however many sets of sides you have on your polygons, it will take that many proportions in order to prove that they are similar or not. So we are going to need to set up 3 different proportions dealing with these 3-sided polygons. Now my basic strategy is this: draw a structure of a proportion, pick a side, and write it down. However, I'm going to give you a little bit of more strategy here right now. Okay, here are the 2 triangles. Okay, so we're going to basically build a structure of a proportion. Okay, and we're going to see what's going to happen here. Now, I said we're going to pick just any side from any triangle that we want. Okay, but I'm going to offer you a strategy. Okay, now I picked on the 4 from the red triangle. Okay, now that's not an accident. I actually did that on purpose. It is my habit. What I will always do is I will pick on the smallest value from the figure on the left. Okay, and what I'm about to do is establish a pattern for how to select the values. Okay, so if you develop your own pattern, it's probably better for you because you're less likely to make a silly mistake or overlook some important information. Okay, now what we're going to do is we're going to find the corresponding side length from the other figure. Okay, now I picked the smallest value from the figure on the left. So what do you suppose the corresponding side length from the figure on the right will be? Okay, it should be also the smallest value. You see what I did there? By picking on a particular characteristic, that being the smallest value, I don't have to worry about where the figure sits or what position it's sitting in, because I matched them up by size. Okay, so I picked the smallest value in the figure on the left, and that corresponded to the smallest value in the figure on the right. So 4 is to 6. Okay, now following the pattern, what we're going to do is we will go back to the first figure and we will get another measurement. Okay, well, what do you think my next measurement's going to be? Well, I've already got the smallest value from the figure on the left, so now I'm going to get the medium-sized side length from the figure on the left, which happens to be the 6. Okay. Now I just need to figure out what does that correspond to from the figure on the right. Well, we got the medium size length from the figure on the left, and that'll correspond to the medium size length, the figure on the right. That will be the 9. Okay. Is this a true proportion? Does 4 over 6 equal 6 over 9? Some people can see this one right away. Some people may need to cross multiply. But when you cross multiply, 4 times 9 is 36. 6 times 6, also 36. We have a true proportion. Okay, that's good. But unfortunately, that is not enough to tell us if we have similar triangles or not. There's still 2 other side lengths to consider. Like I said, it takes just as many proportions as there are side lengths in the figure. The figure has 3 side lengths, so we've got 2 other proportions out there. Okay, but here's where the method comes into play. Okay, I've already compared the smallest lengths to the medium lengths. So I can also compare the medium lengths to the largest lengths, and then I can compare the largest side lengths to the smallest side lengths. Okay, so using the same kind of pattern, I'm able to fill in the rest of the blanks. 6 from the left, medium, corresponds to 9 on the right, also medium. 11 on the left, which is the largest, corresponds to 16.5 on the right, which is the largest. Okay, and again, the largest, 11 and 16.5, are going to equal the smallest, which from the first example we know are 4 and 6. If we cross multiply, check and see if these are true or not. Okay, what we see is that these are all true. Okay, what this means is these triangles might very well be similar. Their side lengths, the corresponding side lengths, are all in proportion from one figure to the other. If we had come across even one of these proportions that did not work out correctly, then the entire answer would be a no. Okay, so let's look at one more example on this whole idea of what corresponds to what. Okay. Now that last one was a little easier, okay, a little easy because the figures were sitting in similar positions to each other. Top did correspond to top and so on, okay. But what if you cannot tell which which side lengths correspond to which other side lengths? Well, this is another reason why I like that idea of figuring out smallest corresponding to smallest, largest corresponding to largest, and so on. Okay, so let's start off. I'm going to pick the smallest value from the figure on the right once again, which would be the 3. What is the 3 going to correspond to on the right? Smallest will correspond to smallest, so the 3 corresponds to the 6. Now I'll come back to the figure on the left. What's the next smallest? After the 3, there is the 5. Okay, so what is going to be the second smallest in the figure on the right? The 5 will correspond to the 10. And you continue the procedure. Next smallest and next smallest. That would be the 6 from the left, the 12 from the right, and that should leave you the largest two side lengths, which would be the 9 and the 17. Okay, so sometimes it's almost impossible to visually identify what's going to be biggest. They do not have to draw figures to scale, so that kind of puts us in a tough spot, but we can outsmart them simply by developing a good system and then sticking to it. Okay, now a little side note here. Some of the same rules are applying as they did with congruent polygons, so some of this will sound familiar. When we name similar polygons, the same rules will apply as they did with congruent polygons. So when we identify what corresponds to what, okay, we will make sure that we list those vertices in corresponding order from one figure to the next. Okay, so if we're going to state that two polygons are similar, obviously we're going to name the type of polygon, that being triangle, quadrilateral, octagon, stuff like that. Okay, let's see if we'll name the type of polygon. We will figure out which vertices are corresponding, and then we will list them in corresponding order. Little side note, extra piece of information here. We have a new symbol for similar, one we have not seen yet this year. Okay, it is pronounced is similar to, and it's like the little squiggle that shows up on the top of the congruent symbol, but we do not get the equal sign underneath it. It's just the squiggle. Okay, so a new symbol there. And lastly, okay, here are two triangles. Okay, I'm going to ask you to try to decide if the following two figures are similar, and if they are, to name them. Okay, so what you need to do is copy down these two triangles. You need to look back at the definition of what it takes to be similar, which is all sets of corresponding angles congruent and all sets of corresponding sides proportional. So you'll need to check and see if your three sets of angles are congruent. You will need to set up three sets of proportions and cross multiply and see if they work out. Okay. Sorry the notes ran a little bit long today. As you know, some things are a little shorter and some things are a little longer. Just take the good with the bad. See if you can work this problem out. Bring your notes with you to class tomorrow, and we will answer this one together and see if you got it right. I appreciate you taking time to get your notes done. Have a good night. I'll see you in class tomorrow.